Welcome back to Engineering Mechanics, Lecture 19. And in Lecture 19, we will focus on internal forces for non-orthogonal hinged frames. And so these non-orthogonal hinged frames is a fancy word for pretty much roof structures and anything else that has non-right-angled corners. So our first objective, therefore, will be to introduce frames without those right angles and then pretty much look at those for the support reactions and the internal forces, as we see here. Ultimately, we want to, of course, draw the internal force diagrams as always, but we want to do that for three different cases really. We want to do that for self-weight, for what's called snow load, and for wind load. All those are three cases that can exist on roof structures, and we will now look at those. And in fact, I will start with the very first case, which is the self-weight. So let's look at self-weight. Before we write anything down, let's observe this. So the self-weight actually acts along the entire length of what's called a rafter or the roof structure, and then that is acting towards the center of the earth. So all these angles, all these arrows are vertical. So note that this is very different from what we have done before. Before, when we saw evenly distributed forces, they were always perpendicular. The force arrows were always perpendicular to the actual beam. And in this case, we are actually not directly dealing with the beam, we're dealing with this rafter, and these force arrows are not directly perpendicular to this. So let's begin to write down some notes here. So first of all, this is self-weight. And in this particular case, for educational reasons, we'll just make it 500 Newton per meter. But please note that this is 500 newtons per meter along this beam and not along this horizontal direction, which could be misleading if you just look at these arrows. And to make our life easy, we have the symmetry 500 Newton per meter also on the other side. And what does that mean? So when do we have these cases? Again, 500 Newton per meter is probably not a very realistic way, but it gets the educational point across. So in reality, this can be much heavier based on the weight of the shingles, for example. Or it could also be the rafters themselves, or insulation panels, just like electrical components, the ductwork, and then also the drywall that's usually hung, or OSB components. So pretty much anything that can cause a load on the roof system. So let's keep in mind that these forces are all identical in the sense that they all act towards the center of Earth, and that they all effectively act along the length of the member. And that takes us back to the structure. So let's take a look at the structure. What do I mean by the member? So we have the member here from node A to node C, and we have the same or similar member from B to C. And so it acts along this line. And now, similar to the frame that we discussed in the last lecture, that was an orthogonal frame, we had a hinge somewhere in the frame. And now we have a hinge at the peak of, or the top of the roof, if you will. And we, of course, therefore must have two pins at A and at B. And so we now need to discuss the support reactions, because before we can analyze any internal forces, we always need to look at the support reactions. And you know from the previous lecture that we effectively have two support reactions. Let's call this here RAY and RBY. And we also must have RAX and RBX. And so it is very common initially to overlook the X components. The vertical is clear because everything that goes up has to come down. So these two balance pretty much everything that comes down. But because of the hinge here, if these were rollers, you can probably imagine that they would just slide out. And therefore we need something to prevent that. So we need RBX and RAX. But what's important for us here for the first non-orthogonal frame that we look at is that it's also a symmetric system. And in fact, it's a very easy symmetric system because it has a length or a triangle of 3, 4, and 5. So the length along that beam is actually 5 meters, right? So we have 5 meters here. And so we can actually say that we have a symmetric system. And because we have a symmetric system, we know that RAY must be equal to RBY. So that is one condition that we can take from the symmetry. And similarly, we can say that RAX is equal to RBX. So that must be true, because otherwise symmetry would not work out. So how much is RAY? That's the easier one to start with. So RAY is pretty much a half of all the vertical loads that come down. Or RAY plus RBY is equal to all the vertical loads. So I can write down here that it is effectively 1/2 times all the self-weight. How much self-weight do I have? I have the 500 Newton per meter over this length of 5 meters, and I have that effectively 2 times. So 1/2 times 2 times 500 Newton per meter multiplied by 5 meters. And so that is exactly how much load we will have, and that is 2.5 kilonewton, or 2,500 Newton, which is equal to 2.5 kilonewton. So that is a good start, because now I know that this one here is 2.5 kilonewton and RBY is also 2.5 kilonewton. But the question now is, how much is RAX and RBX? And if we remember from last class or from our last lecture, when we have systems like these, frames with like a hinge in the middle, or anywhere for that matter, we can always take the sum of the moments about that point and use the condition that the moment is equal to 0 at that hinge. And so therefore I can just take half the system and rotate about C. So I'm going to take the left side here, RAX, which has a lever arm of 4 meters about that point. RAY has a lever arm of 3 meters. And this force here is concentrated in the middle of the 5 meters, but because it's acting perfectly vertical, it has a lever arm of 3/2. But I will write that down for you now. So to calculate RAX, I have to take the sum of the moments about the hinge at C and set it equal to 0. And of course counterclockwise positive. And so I start with my unknown. 0 is equal to RAX multiplied by the lever arm of 4 meters, because that's the shortest distance between that point and the line of action of RAX. So times 4 meters. And the rotation of that RAX that I assume happens to be counterclockwise, therefore that is positive rotation. Then it's also RAY, but I already know that's 2.5 kilonewton. So 2.5 kilonewton multiplied by 3 meters in this case. That's the vertical lever arm. So just to be clear, that's this force about this point with that lever arm. And that rotates actually clockwise, so therefore that is negative. And last but not least, I have to include the 500 newtons, so that's 0.5 kilonewton per meter multiplied by 5 meters. And now careful with the lever arm, because the resultant effectively is acting in the middle and it's vertical, so therefore the distance is 1.5 meters. So 1.5 meters or 3/2, and that is rotating counterclockwise about C, so therefore that is a positive lever arm, if you will. And if I now rearrange all this, then I will end up with this equation down here. And the answer then is 0.9375 kilonewton. And this is not for significant figures, but just to carry our understanding through. It's easier to use these numbers here for this educational example, so that later on we can clearly identify which number belongs where. And due to symmetry, RAX, remember, is also equal to RBX, and now I solved my support reactions. And in fact, I'm going to include that here in my system, so that is 0.9375 kilonewton, and the same is true here, 0.9375 kilonewton. And so I now calculated my support reactions for self-weight of a non-rectangular frame. And that is the first step towards calculating internal forces. Now let's move on to the next issue, and that is, if you calculate internal forces, you need to find the forces that are actually 100% parallel to the member. For the normal forces, it's parallel, and for the shear forces, it's perpendicular. The problem that we currently have is that the support reactions are not. And so what we have to do next is actually break down the support reactions. So our next step is to do the breakdown of these support reactions. And you can already see in the picture here that's already been done, at least conceptually. So let me point towards it. So RAX, which we just calculated, has a component that is perpendicular to the beam, and it has a component that is parallel to the beam. So I'm going to call these RAX parallel and RAX perpendicular. And similarly, RAY parallel and RAY perpendicular. So maybe the first step I should do is bring down my actual results here. And so I had RAY being equal to 2.5 and RAX was equal to 0.9375. All right, now we need to understand how to break them down. And so to do that, I look at my general triangle. Remember, it's a 3, 4, 5 triangle. And so we're going to use this information, the 3, 4, 5 triangle now. I need to pretty much connect which side is which. So let me zoom in first into my standard triangle here. So this I know for sure, and I'm going to call this angle here alpha. And the way I think of this is that alpha connects the 5 and the 3 side, and alpha has nothing to do with the 4 side. So I now have to bring that into my other 2 triangles. And the easier one to see is probably the one for RAX. So let's look at RAX here. RAX is horizontal, and RAX parallel is parallel to the member. So that means that the alpha angle must be situated right here. right? And now the next thing I know is that RAX is the hypotenuse, which is the 5 side, and 5 is connected through alpha with the side that has a length of 3 here. So I know that I have 5 here, 3 here, and by default that makes this the side that is 4. And similarly, I can do something for RAY, but the way that's easiest for me to see actually is if I extend my line that's parallel. So if I have a line that's parallel here, and then I have a horizontal line, then I get easily my alpha again. So here I have alpha, and that alpha has, that triangle that I just drew has a 90-degree angle, and so that turns this into, let's call it beta, and therefore this angle here must be alpha again, right? Because we have the right angle right here. And now I can use the same logic again. I can say, hey, RAY is the side that has 5 long, and alpha connects 5 and 3. So RAY perpendicular is the 3 side, and RAY parallel is the side that has a length of 4. So now I identified my 3, 4, 5 triangles, and now it is actually easy to break down my support reactions. So let's do that. Let's first calculate RAX parallel, and RAX parallel is equal to RAX multiplied by 3 divided by 5, right? So that is here RAX needs to be divided by 5 and multiplied by 3. And so that way I get RAX parallel. To no surprise, it's the quite opposite for RAX perpendicular. So therefore I have RAX times 4 divided by 5. And I can now calculate my final results here. I have to plug in RAX, which is 0.9375. And so I get 0.5625. And I get 0.75. And both of those are in kilonewton. And let's now focus on the triangle down here. So I have RAY, and to calculate the perpendicular part, I have to use 3, and to calculate the parallel part, I have to use 4. So in numbers, that looks as follows. RAY parallel is equal to RAY and multiplied by 4 divided by 5. So that's this component here, the 4 and the 5, and the parallel component is this one. And my RAY perpendicular must be the opposite, of course, RAY multiplied by 3 divided by 5. And so if I solve these, I get effectively 2 kilonewton for the parallel component, and I get 1.5 kilonewton for the perpendicular component. So let me repeat what we've just done. We took the support reactions, the ones that are vertical and horizontal, in a global coordinate system, and broke them down into parallel and perpendicular components. So here's the perpendicular components. In fact, in this picture, the perpendicular components are red and the parallel components are blue. And to do that effectively, I had to use the 3, 4, 5 triangle that tells me exactly how the geometry of the system is arranged. So now you probably see what the issue will be here. We broke it down, but we probably also want to combine them. So for example, the perpendicular components are opposing each other, and I want to know how much there is either, away from the node or towards the node in the combined version of RAX perpendicular and RY perpendicular, and then quite the opposite for RAX parallel and RAY parallel. They both are added together. They both push on the node in the direction of the member. So we now have to bring them together, and we will do that on the next page. So here on the right side, we have that very picture, except that now we only have one parallel component and one perpendicular component. So what I have to do now is I effectively have to collect all my components. And let's do that together. So I need to identify RA parallel. So now that y and x is gone, I'm only looking at RA parallel, and I do that by RA y parallel plus RAX parallel. And if you run the numbers for that, you will end up with 2.5625 kilonewton. Similar for RA perpendicular, except that now they're actually subtractive. So I have RA y perpendicular minus RAX perpendicular. And that is because they were acting opposite to each other. So one of them forces the other one to lose some intensity, if you will. However, they actually turn out to be 0.75 kilonewton. So that is all nice, except let's keep in mind that self-weight also has components that are parallel and that are perpendicular. So we now have to also break those down, and what we effectively will be doing is we will have a vertical force that of course is the hypotenuse, which is 5. Then we have a parallel component, so this is, let's call it F parallel, and then we have a perpendicular component, so this is F perpendicular. And so we need to once again connect our 3, 4, 5 triangle there, but that has already been done down here. So we already know that this is the hypotenuse with 5, and then 4 and 3 is already given with the same logic. So now what I can do next is I can actually calculate my internal forces, or better yet, I can create my functions for the normal force, for the shear force, and later on for the bending moment. So let's look at it for the normal force and shear force. Before I do that, I think it's smart to use my numerical values here and add them. So RAY parallel is 2.2625 and RA perpendicular is 0.75. So let's look at our normal force. So as always, and as we have done before many times, we're just going to set the sum of the forces and x is equal to 0. Just be careful with the x, because x now runs along the dashed fiber. In fact, that's what the dashed fiber always says, that we have to go x positive from the left to the right if the reference fiber is on the bottom. And so I can now set that equal to 0, and I already brought in here my normal forces, or like all my internal forces actually, but I start with my normal force. So it's positive n of x plus 2.5625, that's this guy, And now I have to be careful because I'm missing how much this component from the normal force is. So the 4 part of the triangle. And how do I do that now? I guess it's easiest to have the 500 Newton per meter multiplied by x meters, because keep in mind that x is running in this direction. So this is where x is running now. So x meters. But I also have to account for the part that is only parallel to the member. So what I have to do is divide it by 5 and multiply it by 4. So I'm going to do that now. So multiply by 4 and divide by 5. Last but not least, I have to decide if it's positive or negative. And since my n here is positive to the right, this one is opposing it, and therefore it has to be negative. So now I'm going to have a negative 500x times 4 over 5. And if I solve this now, I probably would do better to turn this into kilonewton. So this here would be 0.5 kilonewton per meter. And now I can combine the units, and I will find that I end up with 0.4x minus 2.565. And of course the whole thing is in kilonewton. And now I created a function for the normal force along the member A to C. And remember that this beam here had a length of 5 meters. So the minimum value I can plug in for x here is 0. And the maximum value I can plug in for x is equal to 5 meters. Also notice that when I plug in 0 for x, that then I will find the support reaction here, or the parallel component, which that must be true too. So if I plug in 0 here, then that is true. I actually get a compression force of 2.2625. So that matches. So with that said, it's probably easy for us now to use the logic for the shear force. So let's look at the shear force. Once again, I set my equation, sum of the forces in the y direction, equal to 0. Y in this case is y as it is defined by the dashed fiber. So now my shear force is actually going down, which is negative, but positive defined shear force. I have 0.75 going up, so therefore that's positive. But I have this component from the 500 Newton per meter going down. Therefore it is negative 500 or 0.5 kilonewton per meter. And that is multiplied by x meters. But once again, I need to break it down to the 3 over 5 component, so times 3 over 5. And if I solve this now, I will find that it's negative 0.3x plus 0.75. And that is in kilonewton. Once again, I can run x from 0 to 5. And if I plug in 0, I need to find 0.75, which is the case here. So that concludes the shear force. And I think we're on a good track here. So let's move on to the bending moment, which is similar to the shear force, except that now we need to consider the lever arm, right? So this force actually now gets a lever arm, which will become tricky. The lever arm for the 0.75 will be easy. So what I will do now, and I need you to understand this, that we're actually taking the sum of the moments about this point, which now is of course running in terms of x. So let's look at that. So my sum of the moments is equal to 0, counterclockwise positive, and my defined moment here is already counterclockwise, therefore positive, positive. And now I have the 0.75 here that is turning about this point. So the perpendicular force here, so this is times x, 0.7. So I need that to be 0.75 kilonewton times x meters. All right. So I have that component covered, and now I have also to include the 0.5 kilonewton per meter times x. So that would be 0.5 kilonewton times x. X is along this direction. And now I have to be careful because I need to account for the lever arm, which is pretty much half the distance along here. But keep in mind that this 3 now needs to be expressed in terms of x, because x technically grows in this direction, and as x grows, the component in the horizontal direction also grows. And so what I will have to do is express this horizontal component in terms of x. And the way I do that is by, of course, my ratio, so times 3 over 5x. But it's only 1/2 of that, right? Because it's the lever arm. So that is effectively the lever arm. And you see that now x is squared in that equation, right? So I have x here, and therefore it's a squared equation, which is good because we know that the moment must be parabolic. So ultimately, it's minus 0.15 x squared plus 0.75 x. And this equation, of course, must be in kilonewton meters. And there you have it. So number one, if I plug in 0 into this equation, then my value has to be 0 because there's a hinge here. I mean, this is only a hint that I give my students, but ultimately there's just a support there. And so the support reactions have no lever arm yet. Therefore, if you plug 0 in, the moment must be 0 at this location. And that is true if I plug this in. Also, what's true is that this equation, the shear force, is the derivative of the moment. And what have I done now? I have on this page effectively my internal forces. And in fact, I don't just have the internal forces, I also have functions for the internal forces for my roof structure. Be careful, it's only for the left side of the roof structure, but with like deep thinking, it's probably easy to also extend the knowledge to the right side. Just don't do it blindly, because the right side obviously is similar, but also with a few tricks. But we will cover that now on the next page. So now I have my diagrams here for each of the load cases, or I guess for each of the force cases, I should say. So let's start by identifying that. So let's start with the normal force, of course in kilonewton. Then we have the shear force, also in kilonewton. And we have the moment in kilonewton meters. All right, and now I remember my equations. So let's start with the normal force up here. My equation, I'm just going to bring that over from my previous page. So that was 0.4x minus 2.5625. And of course, again, kilonewton. So now how do I bring that over into my diagram? So again, here, if I plug in 0, I will actually end up with negative 2.5 something. So what is a negative again? A negative means the side of the dashed fiber or the reference fiber, and it's actually gonna be down here. Notice that this here is a right angle. I will not show this in the future again, but That's like important to understand. It's not like a line's random, it's actually perpendicular to that. And so now I can actually plug in values to my equation here. So I can plug in 1, 2, 3, 4, 5 until I convince myself, or I can understand that there's load pushing here, there's more load pushing here, more load pushing here, more and more and more and more. And so therefore the normal force, the compression, gets more towards the bottom of the rafter. And therefore I have to actually have a slope that decreases towards the top, if you will. So it goes from here to less internal force. And so all I need to do is plug in 5 and then connect my values. If I plug in 5 there, I will end up with a slight value on the top, right? Because the top is a little bit in compression from the other part. So it looks something like this. And in fact, if I plug that in, I end up with a value of minus 0.5625. And now I can connect my dots, if you will. And it makes hopefully perfectly sense that the compression gets more and more as you walk, as you come to the bottom of the rafter, if you will. And now we see that it's actually in compression, and the compression is increasing. And that is towards the bottom of the roof. And notice that it is not 0 at the top, which is actually due to the pitch or the angle of the roof, right? So depending on how it's pitched, the right side pushes on the left side and the left side pushes on the right side. In fact, since we understand that the left side pushes on the right side and the right side pushes on the left side, we are probably able to draw the diagram for the right part now, which is very similar, and you hopefully understand that it is also in compression, so therefore it must be negative on that side. And then it is also negative up here on the top. And then I can connect the dots again. And close my diagram, which now looks like this. And I know that here on the top it's also negative 0.5625. And by the way, on the bottom here and here, it's both minus 2.5625. And now I completed my normal force diagram. Let me highlight again what's important to understand for these diagrams is that these lines on the top and on the bottom are actually perpendicular to the axis of the beam. And I must have higher compression on the bottom than I have on the top because the weight increases towards the bottom, right? So there's like more and more accumulating that's pushing down on the foot of the roof. And here on the top, it's not 0 because the left side pushes on the right side and the right side pushes on the left side. So there's a pre-compression, if you will. And that concludes our normal force diagram. We can do the very same thing now for our shear force diagram. So let's bring over our equation first. It will make our life easier. So V of x was equal to minus 0.3 x plus 0.75 kilonewton. So let's start with that. Remember that I started on the bottom left, so I'm going to use that equation, and if I plug in 0, then I end up with positive 0.75. Positive means opposite to the dashed fiber. So I'm going to call this here plus 0.75. And now, if this is the first time I do this and I'm in doubt, I need to ask myself what's happening. And so therefore I just plug in values for x. So for example, 1, 2, 3, 4, 5, of course with a maximum of 5. But if I plug in 5, I actually end up with negative 0.75. And so that's the value I'm going to use here to draw my diagram. So that would be something like this. And I know that it's pretty much an evenly distributed force on there, although it's acting differently than what we've seen before. But I know that it must be linear, therefore. And so I have a positive area here, and I have the negative components here. And if you paid attention, you see it's no different from any beam that had like self-weight on it before. Now let's think about how we can apply this to the right side of the system. So please note that the system actually is a symmetric system. And remember what we already discovered before, that if the system is symmetric, the shear force system or the shear force diagram is anti-symmetric. So and how does it apply now? So instead of starting at a positive value on the foot, I have a negative value. And then here on the top, I have a positive value. And I can connect the dots again, and I get a very similar picture. I didn't do a very good job drawing this here, but the passing through zero would technically happen right in the middle of the rafter. In fact, V is equal at 0 at x equals to 2.5 meters, which I need for my max min moment. So let's look at that now. Let's look at the moment, but not until we haven't reviewed the shear force diagram again. So again, this equation was valid for this member here, A to C. And when I plug in 0 for x, I end up with 0.75. If I plug in 5, then I end up with minus, so I should probably put the value here, minus 0.75. Whereas on the other side, I have 0.75 and minus 0.75. And why is this? Because my dashed fiber remains on the bottom for this component here. And so the system is symmetric. And by the way, the load case is also symmetric. And because that is the case, the shear force diagram must be anti-symmetric. And where this pass through 0, which is effectively in the middle of the rafter, that's where we find our min and max moments. And we're going to look at that next. Before I do that, I just want to show you that I bring these center points down effectively. But it's important to understand that now I have a perpendicular line which really defines where things are happening. So this would be perpendicular to the rafter itself. And now I can use my basic knowledge about moment diagrams to help me draw this effectively. The very basic thing and first thing I know is that at each hinge or at the supports, I must have a moment that passes through 0. And now I need to decide, do I want a maximum or a minimum? So in other words, a maximum would be here and a minimum would be down here. And the same is true on the other side, minimum down here, maximum here, or maximum being a positive value, minimum being a negative value. And I also know that it's an even distributed force that was acting on this member and on this member. And so I must have a parabolic function here. Also remember, this is a linear function. This is a linear function in the shear force. Therefore, this must be parabolic, and the same is true here. Last thing now is positive or negative. So effectively, do I draw my arch this way or this way? And the answer is easy. If you remember, the compression on the top, tension on the bottom is a positive moment. That is exactly what we have here, or as we called it in the class, the beam is smiling. So this beam here is literally smiling. It wants to bow down, and because it wants to bow down, the moment is positive. And so I can now easily draw my moment. So my parabola would sit like this, and same on the other side. So there you have the parabolic function with an m max here and I m max here. We will calculate that m max in just a second. But this is positive, and this is positive. And of course, this is an x square function and an x square function. And we just have to decide how we calculate that. But it's actually very easy in this case because we already calculated m of x. And m of x was equal to negative 0.15x plus 0.75x. And all I have to do now to calculate my maximum is include like the fact that my shear force passes through 0 at 2.5 meters. So where v equals to 0. And last but not least, we also already talked about the fact that we have positive bending moment. So this is positive bending moment because we have a smiling beam, if you will. So beam is smiling throughout entire lengths. And so you see now that we actually completed all 3 diagrams for a non-rectangular frame with self-weight on it. And once again, the logic is no different. What was challenging here for this problem was to first find the support reactions. And after we find the support reaction, we had to break them down into parallel component and perpendicular component. And then we created these functions, and these functions helped us to really draw the system. Again, for a beginner, it's probably tricky to bring the logic from the left side over to the right side, but that's what practice is for and the homework problems. So here I'm not going to focus on the right side, or like not to explain like how that really works. When in doubt, always make a cut wherever you want to do it, or like create the same function for the other side. It might be a little bit tricky because you want to start from the left side if you create a function here, but the same principles will always work. So, and most important for these diagrams to recap is that the normal force increases towards the bottom, makes sense. Shear force is symmetric, and shear force is anti-symmetric because the system was symmetric, and the moment therefore must be symmetric and also positive because each of these 2 rafters wants to bow down, and therefore it must be positive. So that concludes the analysis for the self-weight on a hinged frame with non-right angled corners. And next up we would be looking at snow loads, which is not very different. We're going to do that separately, but the concept will be the same after some initial massaging of the snow load. So let's do that next. So snow load is a very particular thing because it's actually projected loads, and if you can see this here, so there are these dashed dotted lines here, if you will, that signify that the snow load here is actually acting over a length of 3 meters, but is actually projected down onto the rafter. And that is a little bit tricky for a beginner, but we will break that down right now. And to make our life easy or comparable, we will use 500 Newton per meter for the snow load as well. And let me just clarify, for educational reasons, I put a little gap here to make sure that we understand that there's something acting on the left and on the right, and it's not like, there's no continuation from left to right, but in reality, no engineer would take the time to break this up. You would just draw a solid line throughout here, and you would look at it as 500 newtons per meter. Let us talk real quick about snow loads as a concept, and let's understand that it is actually projected loads. So we call that due to projected loads. And that, of course, is mostly snow, which, of course, acts towards the center of the Earth as well, but it actually acts along the footprint or the projection. So the projection or footprint. What do I mean by that? I mean that the 500 Newton per meter is acting here over a length of 3 meters, but think of it as each arrow touching the rafter. So if I try to symbolize that for you or visualize that for you, then we would end up with an arrow down here, an arrow down here, here, and so on and so forth. And so each of these arrows, which originally is acting over a length of 3 meters, has to be brought down to this length of the rafter. So now you may ask yourself, why is this done? Why can I not just use self-weight here? Or why can I not just directly convert this 500 along something that matches this slope? And the reason for that is very simple. Snow loads are given in big manuals for different elevations across the world, or in this case for the United States. And you may imagine that, for example, Florida has very different snow loads than Colorado, and other states have different snow loads. And in fact, in Colorado, different regions have different snow loads, or different elevations have different snow loads. And because when they create these snow loads, nobody wants to tell you anything about how your roof is pitched, right? Because the architect decides that in a sense, or maybe the engineer, but the snow is always defined based on geographic locations, and so it's always based on the projected footprint that the snow produces. And usually, of course, it's not given in Newton per meter, it's actually given in Newton per square meter or something like that, but I took that out here for the concept of this class. Or I guess in the US it's usually given in pounds per square foot, but an engineer would ultimately convert it into pounds per linear foot so that you could apply it to each individual rafter, if you will. So if you understand that, then all you have to do is convert the snow load to a self-weight, if you will, because you see again that we have pretty much forces that are perpendicular. And maybe I draw this here on the other side. So let's take this arrow. So of course, ultimately, we want something that's perpendicular to the rafter and something that is parallel to the rafter. So that would be here. So we have such a force system, and this would be the parallel component, and this would be the perpendicular component. And once I broke that down, then I'm actually at the same case that I had before. However, let's look at this in more detail. So once again, our system is symmetric, and because it's symmetric, RAY is equal to RBY, no different than before. Similarly, RAX is equal to RBX. And so how much load do we have in total? The entire system has a weight of 500 Newton per meter. Now be careful, multiplied by 3 meters. that's all that comes down, times 2. But each RAY and RAX is also sharing the load, so times 1/2. So this of course cancels out. And that is also equal to RBX. Ultimately, RBX and RAX are equal to 1.5 kilonewton, as that is the load that the snow produces on each side of the roof. So now we have the same problem as before. We have two support reactions, right? RAY, RBY, and we also have RAX and RBX. And RAY and RBY we just calculated. So I actually made a mistake here. Let me fix that. So this is not RBX, it should be RBY. RBY, that's the vertical load. And so now I can calculate RAY, which is pretty much done with a similar method as before. So I take the sum of the moments about the hinge, right? So sum of the moments about the hinge is equal to 0. And the hinge actually is at C, by the way, counterclockwise positive. So 0 is equal to, I start with my unknown, RAX multiplied by 4 meters, which is turning counterclockwise, therefore it's positive. I have my RAY, which I already calculated, 1.5 kilonewton multiplied by 3 meters. And now there's many ways of how you can do this. Well, first of all, let's assign a direction. RAY is turning clockwise, therefore it's negative. But last but not least, I need to include my snow load, which is 0.5 kilonewton per meter. And I have to multiply that by 3 meters. And that lever arm now is 3/2 meters. So let's point towards that. So the 500 here is multiplied by 3 meters. That's the distance here. And the centroid of that is acting right in the center, which happens to be 1.5 meters or 3/2 away from C. Because remember, we're taking the sum of the moments about point C. And last but not least, it's turning counterclockwise, therefore it's positive. And so now I created my full equilibrium equation, which now means that RAX is equal to 4.5 minus 2.25 divided by 4. So ultimately, RAX is equal to 0.5625 kilonewton. And that also happens to be equal to RBX. Remember the symmetry. So now we are actually at the same point where we were before. Almost, except remember this part here, this triangle here. We will have to deal with that later again. But the logic is no different than before. We now need to go ahead and turn these forces all into parallel and perpendicular components. In fact, we'll do that next. Let me just repeat real quick for the snow load that it is a projected force because that is dependent on geography and intensity of snowfall, and nobody knows how your roof will be pitched, right? So you can imagine that if you have a flatter roof, you have more snow to withstand per length of rafter, whereas if you have like a steeper pitched roof, you of course have snow that is easier to slide down, or like you hold less of it on there. And so it is different way of looking at loads. But once again, the loads of course point towards the center of the earth because snow is also affected by gravity. But enough about the enough about the snow load itself. Let's now move on to our support reactions. And once again, we do the breakdown of the support reaction, which now I don't have to explain as much in detail, but once again, I will break down the long side to a parallel and perpendicular component. So here's the parallel, here's the perpendicular, same here, parallel, perpendicular. And just as before, I will assign my angle alpha here, which is here, and then therefore I also have angle alpha here. And if that was too fast for you, please see what we did for the self-weight. We used it there as well. So now I can assign my 3, 4, 5s. So here I have 5. So here I have 5. 5 connects 3 over alpha. So this is 3, this is 4. And again, 5. And alpha connects to 3. And then here I have 4. And so now I can calculate my support reactions. And maybe I will help myself here by adding the support reactions. RAY is equal to 1.5. Whereas RAX is equal to 0.5625. So let's do that. Let's do the math. RAX parallel is equal to RAX multiplied by 3 divided by 5. RAX perpendicular is RAX multiplied by 4 divided by 5. And if you solve these numerically, you find 0.3375 kilonewton and 0.45 kilonewton. Now let's do RAY parallel and RAY perpendicular. And that is very similar again. RAY times 4 over 5 and RAY times 3 over 5. No different from what we did for the self-weight. But if you plug in the numbers, then you will find that we're looking at 1.2 kilonewton and 0.9 kilonewton. So that was the breakdown of the support reactions, which now I'm a little bit faster here because we talked about it in the self-weight. So I can move on now to do the same thing that I did before, right? Remember that we now need to combine the perpendicular components and we need to combine the parallel components to end up with an easier calculatable system. So let's move on to the next page. So I collect all my components, and if I do that, then I will find that RAY, or I guess I should call it RA parallel, is actually equal to RAY parallel plus RAX parallel. And that happens to be 1.537. For RA perpendicular, I have to be careful because they are subtractive once again. So I start out with RAY perpendicular minus RAX perpendicular. And if you plug in those values, then you will end up with 0.45 kilonewton. But just like self-weight, we now have the problem that the snow load also has parallel and perpendicular components, and I will sketch that for you. So we cannot deal with only the force that is going down. We also need to break that down into parts that are parallel and parts that are perpendicular. And so once again, we will break it down for us. And I believe that has already been shown here in this picture on the bottom. So here's my 5, 4, 3 triangle. And of course, you would have to usually figure that out yourself, the 5, 4, 3, but I showed you already how that's done and where to find the connecting angle. So snow load has components that are parallel and perpendicular as well. And I need to consider that now. So let's look at it. Let's start with the normal force again. So for the normal force, I am looking at RAX parallel, and this normal force here, I already brought in the internal forces from my note card. So plus NAX plus 1.5375. But now I need to subtract this component here, the 4 component of the 500. So let's look at it. So 0.5 kilonewton per meter multiplied by x meters. And again, now we have to be very careful because the x is actually acting in this direction, right? So, and the 500 is just not given in that direction. So I actually have to consider what I call the footprint, right? So I have 0.5 times x meters, and now I need to multiply that by the footprint, which is actually given here. So this is 3, right? So it's the 3 side of this 5. So x is actually 5 long when the footprint is 3 long. So therefore I'm multiplying this by 3 and dividing it by 5. And that makes perfect sense, right? Because x is always longer than the horizontal. And so this number here makes it always a smaller number because the x is longer. So that's my footprint, but I also need to consider that it's only this component, the parallel component. So I'm not getting away with only this. This is the footprint. In fact, I probably should write this down. So footprint. But I need to get the parallel component. So the parallel component would be 4 divided by 5. So that's the parallel component. And that is, of course, a little bit tricky if you never thought about it, but conceptually not different than anything we've done before. So you can now rearrange this equation, and if you do so, you will end up with 0.24x minus 1.5375. And the whole thing in kilonewton. And that is our normal function. The trick here for the normal function, once again, is to understand that x is actually going along the axis of the member, but the 500 is not given along the axis of the member. So that's a little bit tricky, and that's why we use the footprint up here. And then the second part is that we need to only worry about the parallel component and nothing else. And the parallel component of the 500 is defined in this case by the 4. So now that we have the normal force function, we can do something very similar for the shear force function. And of course, the shear force function is everything perpendicular. So you see, we have to consider this and this component. And of course, our x needs to be properly considered. So first of all, the sum of the forces in y is equal to 0. Shear force is going down, therefore it's negative, down relative to the reference fiber. 0.45 is going up, therefore it's positive. And now I need to subtract this part. So first of all, it's minus, and then I guess I can just start with the 0.5 kilonewton per meter. And I multiply that by x, but x, once again, is going along the axis of the beam. So I need to get the footprint, because the 500 is actually along the footprint. So times 3/5, once again, footprint. And then I need to get the perpendicular component, which is also 3/5. So this is the perpendicular component. So very similar to before, except the other direction, so 90° to the normal force. If I solve this equation, it actually turns out to be negative 0.18x plus 0.45 kilonewton. And now I can move on to the bending moment, which of course is the integration of the shear force. So we can use the same logic there again. Let's do that. So counterclockwise positive, as always. And I already have included my moment here, which is turning counterclockwise. Therefore, it's positive, positive. I have 0.45, which is this force here, times x, right? Because the lever arm, we're turning about this point here again, and x starts here. And so the longer that gets, the longer x gets. And now we need to worry about this component times x. So let's look into that. We need first to create our resultant force, which is very similar to what we did for the shear force. So 0.5 kilonewton per meter multiplied by x meters multiplied by 3/5. And that is similar to what we have done before. We also need to have this is the footprint. And so this entire thing here actually happens to be the resultant force. So that's the resultant force in terms of x. And so now we need a lever arm, right? And the lever arm also must be dependent on x. So x in meters, but again, x is along the beam, but we need only the footprint of that. So times 3/5. And now times 1/2, because the lever arm is always acting in that half distance. So this is the lever. And that is same logic, a little bit further extended. So it might not be easy to digest immediately, but that's the good thing about these videos. You can just go back and see if you understand the shear force. And if you understand the shear force, then the moment should become clear as well. So now I can solve the equation and get my m of x. And my m of x in this case happens to be negative 0.09 x squared plus 0.45 x. And that equation is in kilonewton meters. And that is good because it's a derivative of the integration of the shear force function, so that matches. And if I plug in 0 for those x's, then I end up with 0. So let's recap before we move on real quick. So for the normal force, we needed to turn the snow load into its footprint through the 3/5, right? So That is because this 3 here is really what we're looking at, like how much we need of the 500. We don't need 500 per meter. We only need the part that is 5/3. And then we also only needed the parallel component because we were talking about the normal force. Very similar for the shear force. For the shear force, we needed the perpendicular component. So that is this part here. But again, instead of 500 per meter, so if x is a meter long, this 500 is actually shorter, or the horizontal distance is actually shorter of the 500 Newton per meters. So therefore we use the footprint. And again, this logic is just extended for the moment calculation, where we used pretty much the same first component here. But then, because we are dealing with the moment, we can just take the sum of the moments about that point, which that of course is x times half, because if this distance, the 500 Newton per meter, is half, then this distance x is half as well. Or in other words, if you take the middle of 3 and this being 5, so then you have the middle of 3 and the middle of 5, they both would act at the same distance. And that's how you can take advantage of that in this equation here. So that concludes our equations, and we can now move on to drawing the internal force diagrams. So what I will do next is I will just bring over my equations. So for the normal force equation, I used n of x being equal to 0.24x minus 1.5375, if I'm not mistaken. And it's very similar as we had before, right? So first of all, it's also in kilonewton, but also it's compression throughout the entire roof, and it's increasing towards the bottom. Of the roof, and then it's also not zero at the top because we have the pitch of the roof due to the angle. So that hasn't changed. In fact, if you paid very close attention, you see that this equation, except that the numbers are a little bit different, but the concept of the equation is the same as we had for the self-weight. And this is on purpose here for educational reasons, right? I used the 500 and the 500. Actually, any value would have made the form of the equation the same, no matter what I would have chosen. But since we used 500 for snow load and 500 for self-weight, you see that here for snow load, you actually end up with smaller factors now. And that is because the snow load is distributed over the footprint, and the self-weight actually was acting over the entire length of the beam, so that made that more intense. But I can now draw the normal force diagram just like I drew it before. The concept is the same, and if you don't know, you just plug in your values, but you know this from the self-weight case that it must be linear, it must be increasing towards the bottom. So it looks like this. And while I'm at it, I will do the very same for the other side. 90-degree angles, of course, for those lines. And both are negative because it's compression, compression, compression. And up here I have this. And last but not least, I need my values, which of course here on the bottom is minus 1.5375. And that is here and here. And on the top, I can just plug in x equals to 5, and if I do that, then I will end up with negative 0.3375. Not to forget my identity here in kilonewton, and that is the normal force. I don't think I have to explain much here because it's literally the same thing as we had for the self-weight, except with different values because our equations are a little bit different. Same is true for our shear force. It will be also in kilonewton as before, and we have a shear force function as v of x, which we calculated to be minus 0.18x plus 0.45 kilonewton. And remember that we had a symmetric system, and therefore our shear force is anti-symmetric. And needless to say that the shear force is equal to 0 at x equals to 2.5 meters. So we need that for the moment. But let's look at this before we draw, before we go to the moment. So I will just draw it. But first, notice here that we'll start off with negative x, which if I put 0 in here, then I end up with positive 0.45. So that means here is the left side, and I have to go up, right? Because I have to follow my arrows here. And then I go down, 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 down with a linear function as I show here. So when I want to draw that, it's going to look something like this. There's my positive value. And if I plug in 5 for x into my equation, I will find that it's actually going to negative 0.45. So what I will end up with is a linear function that goes from positive 0.45 to negative 0.45. And now it's anti-symmetric, keep that in mind, right? But everything else stays the same. The logic stays the same, and when in doubt, you just can solve or analyze the support B and then draw the internal forces for that direction. But we already know how it looks like from previous analysis. So here it's positive now, and here it's negative, with of course the same values, minus 0.45 and plus 0.45. So with that said, I can move on to my moment diagram. Just as before and as always, I can bring down my maximum / minimum values, or like where my values will be maximum or minimum. And so I have that intersection there and this intersection. And my moment diagram will be fairly simple to draw now because I know it's 0, I know it's 0, I know it's 0. And remember that snow is also attracted by gravity, just like the self-weight. And therefore, I don't have to change my logic of the beam is smiling or frowning. In fact, it's smiling. Therefore, I must end up with a maximum and a maximum on both sides. And therefore, I have functions that look like this, where there's my maximum in the middle and my moments are positive, positive, and positive right there. So now I'm done. Of course, I still need to calculate my maximum value, but what's easier than calculating a maximum value if you know where it is and if you have a function? Remember that the function was m of x being equal to minus 0.09x squared plus 0.45x. And this, of course, in kilonewton meter. And so if I set my if I want to find my maximum bending at x equals to 2.5 meters, and I plug that in, then I find m max, which actually happens to be 0.563. And of course in kilonewton meter. In fact, I need to show this here, what my graph is. kilonewton meters. And here is no different, plus 0.563. And that concludes my moment diagram. So let's take a look, and maybe for completeness, where V is equal to 0. And of course I have positive bending all the way through. So throughout, because think about it, the snow is just a different way of self-weight on the system. I mean, it's not self-weight, but it acts like self-weight because both of them are actually attracted to the center of Earth, which, by the way, will be different for the next case we're going to talk about, which is wind load. But I will talk about that in a second. Before we do that, let us discuss these again. So normal force increasing downwards, and like every piece of snow adds more and more and more weight here until it's supported. And so this graph makes perfect sense. Shear force diagram has to be linear because effectively there's an evenly distributed force acting on the roof. And because it's a symmetric system, the shear force must be anti-symmetric with a zero pass-through at the middle of the members. And that means that for our moment diagram, we must have a maximum here at the center of the beam, which we calculated simply by plugging in 2.5 to these equations. So these equations can be a blessing, if you will. And with that done, I think we are ready to finalize or pretty much put the internal force diagrams for snow load to rest, and we move on to wind loads. But of course, we will not talk about those in detail here in the lecture. I will leave this up for you for practice, but I want to give you some pointers and hints here. So what you will see is that we have wind load that is slightly different than the cases we dealt with before. And that is because we now dealing with a windward side. So this here would be windward side, and this would be the lee side, or the side that is, against, or like that's under wind suction, if you will. And so you have wind very perfectly perpendicular to the axis of the beam on both sides, but one is pushing on the roof, the other one is pulling on the roof. And this is very typical for wind loads. Of course, it depends highly on the pitch of the roof, but you have wind pushing in on one side and pulling on the other side. And so this is not a symmetric system anymore. It's a little bit more challenging, but also a little bit easier because now all your forces are actually 100% perpendicular to the axis of the beam. So there's no parallel component actually in this case. So that should make the life a little bit easier. Wind, similar to snow loads, is actually defined per geographic regions. In ASCE 7 is the document that defines wind. This is past or beyond the purpose of this class. But based on the geographic region, it tells you how much wind pressure you have and wind suction. Of course, again, it's also dependent on the geometry of the roof, which goes way beyond the purpose of this lecture. But just so you know, that is defined somewhere else. For the purpose of this educational analysis, we're also going to make this here 500 Newton per meter, and we'll make it also 500 Newton per meter on the other side, which would never be the case, or very rarely be the case, that the windward side and the leeward side is identical to each other. But this will make your life a little bit easier. And I will now shy away from solving this for you, but you would first have to calculate your support reactions yourself, right? So you still have the 4 support reactions. Then you would have to break them down. And then, of course, you go through the very same exercise. You define your function n of x, your v of x, and your m of x. And be a little bit careful here because maybe the left side is different than the right side in this case. But ultimately, you can draw your diagrams, and that is the part that I already have done for you. So you see here the normal force is actually a constant in this case, and I'll let you study that, why that is and how that is. And the shear force diagram now. So maybe I'll include that for you, the information that this is shear force and this is in kilonewton. Then this here is the normal force and this is also in kilonewton. And then we have the moment diagram. And notice that the system actually in this case was anti-symmetric. Actually symmetric, and the load case was anti-symmetric. And what that means is that your shear force diagram actually happens to be symmetric in this case. So this is a symmetric shear function or shear diagram, and your moment diagram is actually anti-symmetric in this case. The normal core force is not really affected by this, except of course due to the support reaction and the pitch. There's like an initial value here, but because all the forces are acting perpendicular to the roof, there's no increase or decrease in normal force. And you see the values are given here to you, so you already have the answers. Now it's up to you to really calculate how to get these values and how to reach those diagrams. And I will leave that to you. Before I leave you, however, let's take a look at our checkpoint. So what did I learn? The takeaways, you can fill this out now. What is unclear to you, you should also verbalize to yourself so that you know what questions to ask and where you need to get clarification. But I think the final checkpoint, we can use that to reiterate what we talked about. So we clearly can distinguish between 3 load cases now. We talked about self-weight, snow load, and wind loads. So we saw that the self-weight pretty much is acting along the rafter, the snow load acting along the footprint, and the wind load is acting along the rafter, but 100% perpendicular to it. I also understand the difference of the 3 load cases and how each of them act on the structure and what they effectively do to the structure. So now I can calculate for all these cases, the vertical and horizontal support reaction. That's always where I start. So that's according to a global coordinate system. And then I need to decompose them. So I hope after this lecture I know that how I calculate the vertical and horizontal support reaction and break them down into the parallel and the perpendicular force components. Because without that I cannot move on to actually draw the internal force functions, which now I can also create for roof structures. So with that said, we are ready for the homework. The actual homework problems are very minimal in this case, so don't get scared by all these scary drawings here. But really what's only required for you in the homework is problem A and B. And everything down here is optional. This is just something I added based on student feedback who wanted more practice before they go into the exam. But because this is the last homework before the exam, I don't want you to be overwhelmed with all the work, and I want to give you some freedom to studying what you want to study. If you want to study more on the non-orthogonal frames, then you have problems here that can help you to get a deeper understanding of the subject matter. But really, you only have to turn in these problems. So let's take a look at them. So the first one is fairly obvious based on what we've done in the lecture today. And that is that we have a roof structure with snow load on it. And that was essentially covered. So I believe this will be a good way for you to practice how to find the support reactions and then the functions and the internal forces along the slope members. So I don't think I have to tell you much more about this one. It becomes a little bit more interesting here on the right side, because now we are combining a orthogonal frame corner with a non-orthogonal frame corner. You have the hinge here. So this part effectively acts like one part of the roof structure that we covered today, and this part acts like something we covered in our previous lecture. And so calculate your support reactions first and find your diagrams. Of course, to do that, I say that one last time, you need to identify the reference fiber. So I always put it on the inside, and that would look like this. But you are free to put it wherever you want to, as long as your diagrams match the system or the reference fiber. Now let's take a look at these optional problems. Again, these are not requested of you, but let's start with this one. I think this is an interesting problem because, again, it has a sloped member in it or a non-right-angled corner, but it also has a right-angled corner. And in this case, you actually have a very interesting case where the resultant force of this distributed force passes through this point. So you might be surprised how quickly you can solve this problem if you really take a look at it and see what's going on. In fact, in terms of what's going on, notice that this here is a non-loaded beam, if you want to call it that way, or a column. It's something in between a beam and a column, but it's not loaded. So that is something that actually prepares you for some topics that we cover after the exam, but more on that later. For now, just know there's a hinge here, and there's no load here. So that tells you something about the shear force and the bending moment diagram. And I let you play with that and practice that as an option. Now, this is a problem that has a certain difficulty level. Of course, difficulty is always questionable. If you know it, and then it might not be difficult to you. But my experience is that students perceive this type of problem as difficult, which is also why it's not really included in the homework set. It can take quite some time if you are just learning engineering mechanics. But let me tell you what makes the problem so interesting. So first of all, we have superimposed load case. We have self-weight here, and then we have snow load here on top of it. But we also have a non-right angled corner that has no hinge in it. So you have not seen this so far in this class. So we only had corners like here that had a hinge and then were not orthogonal. So what this means here is that the shear force and the normal force at the corner needs to be translated under the given angle. Whatever angle these values give to you, C and D produce a certain angle here to the horizontal. And so that leads to a transmission of the shear force and the normal force at that corner. That is technically beyond the purpose of this class, but if you really want to learn engineering mechanics, and for example, if you're a mechanical engineer or civil engineer, you definitely want to get a deep understanding of that, and I invite you to look into that. Again, this is optional, so challenge yourself if you like. If you're completely overwhelmed already, just don't do it. It's fine. This is just an opportunity that I added based on student feedback. Students said they wanted more of these types of problems, and they wanted something that really shows them the challenge as it could be in the real world. And so you could see something like this at a very difficult level in the real world. But that concludes the homework here. I wish you good luck studying that. Again, this is the last homework before the upcoming exam. So take this as an opportunity to practice and take this as an incentive to get you ready for your upcoming challenges when you really need to perform under time pressure. But of course, after all this homework, you should be really well prepared, and I hope that you will ace the upcoming exam. I have no doubt you can if you want to. So please want to, and I wish you good luck with that. I see you in the exam and in one of our following lectures. Until then, stay safe.